So here is a single degree of freedom system and I'm just shaking it at the base. And as you can see that it just behaves like we would think it would. And it's whenever the forcing frequency is resonating with the single degree of freedom system, it's actually showing too much dynamic amplification. But what happens when we add a tune mass system? And as I attach and shake, you will see that there is a significant reduction in the dynamic amplification of the primary structure, even though the frequency of the excitation is still pretty much the same. And as we move on, I'm actually now changing the frequency of the base excitation, and the primary structure has stopped moving, and then suddenly the entire system resonates with the external force. Then it again starts moving, but still the dynamic amplification is nowhere close to 6. So let's take a look at physics that goes behind this.
So let's take a look at mathematics behind a tune mass system, not a damper, because we'll study about it later on. So here in the picture what I have shown is a coupled system with a main mass capital M, which is attached to a secondary system with a mass small m, and both have a stiffness of capital K and small k respectively. So we'll call this entire system as primary structure, and the smaller system will be known as a tuned mass system. Why a tuned mass? We'll discuss about it later on. Let's first figure out how a 2 degree of freedom system responds or interact with each other. So what we are looking at is a harmonic excitation on the main mass M. You can imagine it as a wind force acting on a tall building, and we already saw in previous videos how it affects, how the wind forces and the vortices affects a very tall and slender structure. So you can imagine this force as the exact same thing as a harmonic excitation on a slender building. If I draw a free body diagram of the main mass M after attaching it to the secondary mass small m, we know that there is an harmonic excitation P0 sin omega t. Let's consider it as in positive direction. If we try to push any object, there is an inertial force that acts in opposite direction. That's called mx double dot. That's the mass of the system times the acceleration. Now there was a spring attached behind this mass m, capital K. So once we push the system this way, spring will be pulling back the mass in this direction. So that's why it's kx1. And the other spring that is in front of the capital mass M will be compressed, and the compression force will be equal to K displacement of relative displacement between the main mass and the secondary mass. So from that equilibrium, I can write down the equation as mx double dot plus K plus small k x1 minus kx2 equal to the external force acting on the main mass M. For the secondary mass, there is no external force acting. The only thing that's resisting is the secondary spring force that was in compression as we looked before. So that compression will cause this mass to push in this direction. So that's k x1 minus x2. And the inertial force will be resisting the system's movement. So that's mx2 double dot. And that equilibrium can be written down in this form. Let's say that the harmonic excitation is represented as A1 sin omega t for mass capital M and A2 sin omega t for mass small m, secondary mass. If I differentiate it twice, I get this. It's a very basic differential equation. And similarly for the secondary mass, it's x2 is equal to minus A2 omega square sin omega t. What I did is I just replaced all x1 double dot value into the main equation, and in the end I get an equation that looks something like this. Now we know that in any equation a sinusoidal force, so the sinusoid cannot be zero. It varies on the basis of the external force excitation. So to satisfy the equilibrium, we know that the coefficients of these equations should be equal, or else it cannot be satisfied. Once I make the coefficients equal, we come up with this equation for P naught, and similarly for mass small m we come up with this equation. What I'm looking for is the solution of these two equations in terms of the excitation and the amplification of the excitation because of resonance. So these are the exact two equations, and what we'll be looking at is we want to make it simpler in terms of just frequency, natural frequency of the primary structure and natural frequency of the TMD. So we are just doing that by replacing the ratio of capital K over capital M with capital omega and small k over small m with a small omega, and xst is equal to P naught over K. You can consider it as a static displacement. So instead of a resonating force that varies on the basis of the natural frequency of the force, let's say if I just apply a force P naught instead of P naught sine omega t, a structure will displace on the basis of its stiffness. Now that will be known as the static displacement. So that term is important because over here we are interested in the amplification of the static displacement because of a resonating force. And if you want to understand more about amplification factor, you can actually watch our video on resonance and amplification that we posted before. So once I do that, what I come up with is these two expressions, and these two expressions tells me that there is a relationship between A1, A2 and a static displacement of the system. And from the second equation, it's very clear that A1 will be equal to A2 times 1 minus omega square over omega A square. This relationship is very important. It tells me that A1 displaces in some proportion to A2. It's not just a random excitation anymore. So once we solve that for A1 and A2, we get an amplification factor. That's this. Remember, it's the actual displacement over the static displacement. That's called the amplification factor. And since the structure is elastic, more the static displacement, the more will be the actual stresses in the buildings and the structural systems. So once we have these two equations, we want to understand how these two equations affect the system. So for that, what we have done is we have created a spreadsheet which you can play with. We'll be attaching the link to the spreadsheet in the description. And you can use that spreadsheet to understand how, by varying different frequencies of the TMD as well as main mass and changing the stiffness of the system, how the entire amplification factor gets affected, because that's the only thing we are interested in studying in. And the beauty of tuned mass system is, if we select the natural frequency of the secondary system such that the natural frequency of the TMD resonates with the frequency of the exciting force, the end result is the main mass remains static. It doesn't move at all, because all the natural frequency excitation coming from the external force will be absorbed by the natural frequency movement of the TMD. So the TMD will move a lot, but the main structure will not move at all. And that's reflected from this graph. You see, there is a resonating frequency for the combined system of TMD and the primary structure. And this is the actual displacement of static primary structure over the static displacement of primary structure. And as the omega over omega n, so the exciting frequency over the natural frequency of the system varies, there is a changing dynamic amplification factor of this coupled system. And at one point in the entire graph, you can see that there is a point where there is no displacement of the main mass, and that's what we call the tuning of the combined system. And that tuning is achieved on the basis of understanding the frequency of the exciting force, understanding the frequency of the main mass, and actually calibrating our secondary mass so that it actually resonates with the main mass. And once we calibrate it in this manner, we get a system that is known as tuned mass system. So let's go ahead and play with our Excel spreadsheet and see how changing the frequencies and changing the mass of the secondary structure affects the overall response of the coupled behavior.
So in this spreadsheet, what you can play with is 4 different parameters for a 2 degree of freedom system. The first couple of parameters are the natural frequency of the tune mass damper, and the second parameter is the natural frequency of the main system, primary structure, as well as the stiffness of the secondary system or a tune mass damper and the stiffness of the primary structure. I've written down the basic equations that I actually showed before. These equations are again the same. It's presenting the dynamic amplification of the primary system. That's the first equation, and the second equation is the dynamic amplification of secondary system. Now, why dynamic amplification is important to study? So as we discussed before, in an elastic system, stress is proportional to strain. So if you have more dynamic amplification, that means your system is displacing that much more, and at resonance without any damping, it can go to infinity. That means the structure will break. So that's what dynamic amplification tells us. So more the displacement means more the strain in the system, and from the proportion of stress equal to strain, more the strain means more will be the stresses. That means more loads in the system. Now, there is an ingenious way to reduce these loads is taking advantage of this secondary system and tuning it. This word tuning is very important. Tuning it so that the response or the amplitude of the primary structure reduces close to zero. That can be achieved only by varying certain parameters for the tune mass damper such that it kind of resonates with either the exciting force, that's the external force P naught sine omega t, or it resonates with both the main structure as well as the exciting force. So in case of wind, a structure oscillates back and forth only at its natural frequency. So the excitation is occurring at natural frequency. Now, if we calibrate the tune mass damper to the natural frequency of the structural system, just like in case of type A 101, what you can achieve is, even at very high external functions that are trying to excite the structure will not move at all, surprisingly. It will be damper inside the structure that will be moving. So if you are standing on the floor of the structure, let's say on 88th story of type A 101, you will not feel any accelerations. But when you look at the damper is moving. So that's the fascinating thing about tune mass damper. Now here, let's say if I shift the natural frequency of tune mass damper way away from the natural frequency of the structural system or the primary structure, you see that it doesn't create that much impact. It does to a bit because now the combined system is not resonating at the frequency of primary structure, but it's resonating at about 1.25 times the natural frequency of the primary structure. And that's only because we have calibrated the TMD in such a way. And it could be a little bit harmful if we don't understand what will be the frequency of exciting function. But for wind, it's very simple. If I just calibrate it and make sure that the frequency of TMD is matching the frequency of the primary system, I get a very beautiful band, and at the natural frequency of primary structure, I see that there is zero displacement. The primary structure doesn't move at all. but at the same time there is a movement in the tune mass damper, and that's fine because tune mass damper is designed for absorbing these loads, and it's there so that it provides more human comfort, so that building doesn't move and we don't feel any accelerations. So that's okay, we can account for this displacement inside the building itself. And the other thing to notice is now there are two exciting frequencies, or the resonating frequencies, instead of just one. First one occurs at somewhat between 0.5 and 1, so that's 0.5 times the natural frequency of primary structure and natural frequency of primary structure, and the other resonance occurs between 1 to 1.5 as it is visible over here. So if we are outside these resonating frequencies, then for sure our damper is going to reduce the loads in the primary system. But for example, let's say the forcing function is occurring at this frequency. You know what we can do? There is an ingenious way. You can just straight away lock the damper, and now the frequency of this system won't be over here, it will be somewhere at this point, and that will let us move away from the frequency of the exciting function. So that's how tune mass damper can help us, and with today's computation we can either switch it on, switch it off on the basis of the accelerations that the primary structure is experiencing. Now this, you can play with 4 different parameters, understand how stiffness of the damper and stiffness of the system also affect. For example, if damper doesn't have any stiffness, you see this band becomes very narrow, and that's because if damper doesn't have stiffness, it's not going to get excited so easily, and it's not going to absorb that much load. But let's say if it's exactly opposite, damper has too much stiffness and primary structure doesn't, and it's like putting your building on top of like 4 jelly beans or even gummy bears. Like the building itself is so soft like gummy bears, and on top of that you put a wood block, so even if you shake it, it's not going to do anything because gummy bears are just going to deform. So that's why it's important to actually see, okay, what's the stiffness of the primary structure and what should be the stiffness of the tune mass damper. Now the other tab just talks about omega A, that's the frequency of the damper, and mu. Mu is the ratio of the mass of the tune mass damper over the mass of the primary structure, which is also equal to the stiffness of the tune mass damper over the stiffness of primary structure. Now if we go back and take a look at the equation that describes the natural frequency of the system, it's equal to K over M. Now because they both are ratioed the same over here, I can safely say that the tune mass damper is resonating with the primary structure, correct? Now let's say, even if I change this thing, you'll see that the graph doesn't change at all, because forever the tune mass damper and primary structure are resonating with each other, so this graph isn't going to shift. But with changing in the ratio of mass of the tune mass damper over the mass of the primary structure, this band widens. So the lower the ratio of the two, the narrower the band, where you can get a point of 0 amplitude in the primary structure. But as you increase the mass of tune mass damper, this band becomes wider, and this shows the combined natural frequencies. So the first frequency is right there, natural frequency of combined system. The second frequency is right there, and this is a plot of ratio of masses over, and on the y-axis it's the exciting frequency over the natural frequency of the system. So you can see as mu reduces, the two natural frequencies come closer and closer to each other, so you have a very short window to tune your damper to. Now it's very intuitive. Why does this happen? as you increase the mass of the tuned mass damper, what happens along with it is it can absorb more energy and at a wider frequency, because this is the frequency of combined system. So as your tuned mass damper's mass increases, the total mass of the system increases. And as the total mass of system increases, it leads to this increase in couple of natural frequencies of system. So the first natural frequency at mu equal to 1 will occur somewhere at like 0.7 or so, or 0.6, and the second natural frequency will be somewhere about at 1.6 or so. So instead of having a resonating force at 1.0, that's omega over capital Omega, exciting frequency over the frequency of the primary structure, instead of that point, it shifts wider apart. This kind of behaves as a 2 degree of freedom system, or it is a 2 degree of freedom system. But the only thing is, both the mass have significant influence on the entire system. While if you change it to mu equal to 0.01, it's the influence of primary structure that is like governing the response of the entire system. And you can see that they are approaching closer to 1, which all makes sense. So I'm attaching the link where you can download the spreadsheet and play with it so that you can understand how you can tune the damper and how this entire excitation works. And if you go back in our video where I showed you the actual structure moving back and forth with the damper, there was a point in the video where you notice that the primary structure isn't moving at all. And that's because the frequency of excitation was matching the frequency of the tuned mass damper. And it was damper which was absorbing all the loads, and the primary structure was not moving at all. So I hope I cleared some concepts about a tuned mass system over here. What we'll be looking at in our next video is, when you add a damper, what happens to this entire system. Now, if you want to go back and read about damping concepts, you can watch our video on dynamic amplification and damping, and you can clearly see that as you add more damping in the system, the peak of resonance reduces because damper is now dissipating so much more energy. So till then, play with the spreadsheet, read through our blog post to understand more about resonance, and watch our video carefully to understand how a tuned mass damper and the physics behind it. So take care guys, I'll see you in next week. Bye bye.